Of the pose like that. You had to do it to him, boy, the whole time.
I just unmuted you when you started that.
Nice.
Hello everyone. This is MSQ back. It's been a while. Oh my gosh, I'm gonna get feedback on my phone. Okay. Hello. We're back, and we have another math talk ready for you. Right before the term break, we have our social director Shawn McAdam with us, a third-year math comp sci major, double major, who's done summer research under Dr. Raymond Spiteri, and he'll tell us that he's the most powerful exec of MSQ'd, and he's also a multi-talented, multi-instrumental musician with violin and bagpipe in his repertoire. But I will let Shawn take it away with his Inventing the Factorial Function talk. Oh yeah, and by the way, if you want to ask Shawn a question, you can write in chat, or you can join the question queue voice chat in Discord if you just want to have like a little dialogue with Shawn. But if not, I will be sending the message directly to Shawn through voice. Okay, so Shawn, you can take it away.
All right. Stream is just loading. So, I talk about inventing the Factorial function. So today we're going to be learning a bit about invention. We're going to be learning a bit about finding the best fit for our needs, things along those lines. And then also we're going to see how we might go about making something new out of a discrete, maybe the proper word for that would be interpolation. So to kick things off, I have a little animation here. Just put this full screen of what a possible factorial function might look like. I'll go into more detail about what is going on here at the moment. You might think a little crazy, some wacky behavior on the left side. But yeah, we'll get into that. To talk a bit about the definition of a factorial. So this is the product of all the whole numbers between 1 and n, where n is any number. So you have n, n minus 1, n minus 2, up to 1. You can keep that going, but if you notice, we have this recurrence relation. As right over here is n minus 1 factorial, the product of all the whole numbers between n minus 1 and 1. So we have this nice recurrence relation. To plug in a number here, we have 3 factorial equal to 3 times 2 factorial, which is 3 times 2 times 1 factorial, and it's 6. And now you can use this to see when you plug in 1, you get 1 equal to 1 factorial equal to 1 times 0 factorial. So we have proven 0 factorial equals 1, which I think is a bit fun. It's moving us in the right direction for what I want to talk about later. So imagine you have that all figured out, and then you type in x factorial into Desmos to see what goes on. Imagine also that you are a young, feeble computer science student. Even worse yet. This is kind of a frightening looking thing. A lot more than you might be asking for, given the simple premise earlier. And, of course, we'll get into that. There's a lot of complexity to build up to here. To talk a bit more about the history of the problem here, it originated in a series of letters between Leonhard Euler and Christian Goldbach. I'm sure you know lots about, or you've heard Euler's name throughout mathematics. Whereas Christian Goldbach, I didn't know about him earlier. He is the guy who he is the same guy who created a very interesting conjecture in number theory, which is still unproven to this day. And so Euler is credited for the popular solution, often called the Euler gamma function. I know I'm pronouncing that wrong. But here is also another possible solution to this problem. Woefully terrible, though. As you can see, I have it plotted on Desmos. It's constant everywhere in between the little slices, which is kind of stinky because, well, it's not very fun to deal with these jump discontinuities. And also, for 18th century mathematicians, this trivial solution wasn't a function. What they were looking for, specifically what Euler was looking for when he was doing his original search, was just one formula to describe the factorial over its entire domain. which in this new case would be all of the real numbers. So like a half, a square root 2, so on and so forth. So in order to make 18th century mathematicians happy, we will need it to not be piecewise, and we can use all our elementary functions as well as some of the tools of limits, integrals, sums, and so on. To make ourselves happy, it would be very nice if the factorial is tractable. First of all, I would really like to be able to compute with it to begin with. And not piecewise is a big one. If you're doing proofs and things like that, piecewise functions get kind of heavy to deal with. And then there's also some quality of life things, like maybe it's continuous, maybe it's differentiable, or simple, possibly. If it only takes me a few strokes of my pencil to write it down, I'll be happy. But we can still have some fun. Specifically, I'm going to talk about this whole piecewise business, because there's a lot more we can do with that. Specifically looking at if we have a function that satisfies a factorial property, namely f of x equal to x times f of x minus 1, which is the same property that we saw when x was a discrete variable, like an integer or a whole number. And so if we continue this out until giving you x minus 1, f of x minus 2, so on and so forth, until x minus n is between 0, 1, we see this interesting property where if x is positive, we can extrapolate information about the domain on 0, 1 into the rest of the positive real numbers. So that's interesting. If we define f on 0, 1, we have all the positive x values already figured out for us. And now, going in the opposite direction, we can divide. We can take that original property, sub in x plus 1 for x, and then isolate for f of x again. And we get that if x is negative, we can repeatedly divide. And we continue this out once again until x plus n is in 0, 1. So we have another way of extrapolating information about 0, 1 into the rest of the real numbers. So we just need to define x factorial on 0, 1. Now, what would a factorialified function look like? If we did this with any old function, I could think of like a bunch of functions that could possibly fit this factorial definition if I just need it to work on 0, 1. And so here, that original video that I showed you is a factorialified function. It's the function defined on 0, 1 to be 1. It's the constant function here. And you can see it doesn't change upon 0, 1. The problem with that, though, is you see there are little edges all across. Every time we hit an integer, the rule defining f changes. Of these little spots where it is not differentiable. Excuse me. So how do we go about fixing that? That's just an exercise in calculus. We need f to have a continuous derivative at the endpoints of 0, 1. So you can set these limits equal and then do some algebra to solve that. Here you see that this limit as x goes to 1 from the right gets simplified to x goes to 0 from the right. And then we have this little interesting formula, which I have solved ahead of time and plotted. And we see a continuous function. I have zoomed in 0, 1 here to watch how a definition on 0, 1 affects the rest of the graph. And all of these functions that I'm cycling right now are valid definitions for the factorial. They do the factorial things, and, well, yes, they do the factorial things, hit all the factorial's values. And if that's all you're looking for, this is awesome. We may have already solved the problem with infinitely many solutions. Something else that I'd like to note, however, is if we look at the concavity of these things, specifically the logarithmic concavity, we see some really crazy behavior. It just shoots up in really weird ways. And originally, Manum was not very okay with this when I was doing it. I have this funky system with divided differences, computing the second derivative, and also the logarithmic function is not very happy with negative values for arguments. So we just deal with it. This is what McAdam gave me, and I'm happy with it. So we see, to summarize, we need to define x factorial's behavior on 0, 1, use this rule to give us the rest of x factorial's behavior. But there's also a lot of ways to fill in 0, 1. Which way is the best way? It's really hard to know. But with this third property, we know that it's really hard, even impossible, to make the logarithm of f of x concave up for all x positive. And I have a little demo of what that would mean, actually really far in later on in the talk, but we'll get to that. And so because I think it would be fun, if anyone in chat gives me a function defined on 0, 1, any function at all, I will plot it, put it into McAdam, see what it spits out. So, Braden, keep watchful for that. Just any function that's defined on 0, 1, it can have discontinuities, it can be crazy. I'm ready for anything. But while we wait for that, I'd like to also talk about what's going on for the rest of the talk. We'll need to develop some more tools in order to fully understand Euler's solution to this problem and why it looks the way it does, why we might like his definition as opposed to all the ones that I showed you earlier, or one that might be coming in chat later. So, in order to understand all that, we need to develop some tools. Then we need to go factorial hunting. And then I have some really fun applications for you guys involving trigonometric functions. And might even have something pie flavored, because I know Pi Day is coming up soon. Our big goal for the rest of this talk is to compute derivatives of expressions like this. Improper integrals of functions defined with two variables. Keeping x as an argument. So you can note in an expression like this, we kill the variable by integrating over that domain. I have a little demo of what that might look like, but I'll need your imaginations a bit for that. So how would we understand a function like f of alpha equal to the integral from c to infinity of e to the negative alpha t dt, where e is Euler's constant, and you have that nice exponential function. So how would alpha positive change? And of course, you need alpha to be positive in order for this integral to converge. I didn't note it, but c also needs to be positive as well. So here, I have a Geogebra demo, which I think is really cool because once it loads, I can actually interact with it and move it around. So here's the function that I was talking about earlier, e to the negative xt, which we need to integrate over. And so you can imagine the process of integrating this function would be we fix some point, say 1, and integrate over this entire plane. We'd find the area under this curve. So you can imagine taking a slice and doing your regular Riemann integration under that curve. So there's no crazy rectangles or multivariable calculus tools involved. It's just the single variable calculus tools that we know and love, applied to a function that changes as we change the input, moving along this domain. So standard techniques of integration tell us that this integral equals 1 over alpha. This c should be a 0, actually. It really should be a 0 for this to be true. Let's pretend that c is 0 and march on forward. What can we say about the derivative of this function? Like, I can take the derivative of 1 over alpha just fine. On the left, that is a-okay. But on the right, a little awkward to deal with the derivative of an integral. Like, without any further tools, all we're dealing with is just what's going on the left side there. So what if we use some non-standard techniques of integration and just swap the two? What happens then? Is it okay? Am I breaking a rule? Really not sure, honestly. Well, that's a lie. I do know. So we continue marching forward after swapping the integral sign and say integrate this function. Does it equal negative 1 over alpha squared, the derivative of the left side from earlier? Does this equal this? Once again, taking c to be 0, because a little typo there. Yes, we can. In this case, it works out perfectly, which is a little strange if you haven't seen these types of techniques in your Calc 3, Calc 4, or further classes. Is it really okay to just swap the integral sign? Will we need like that? Is this rate of change of the area under a curve function really proportional to the way the curve changes? In this case, yes. How far can we go, though? Can we take the derivative n times, where n is any number? Just keep on going. Have we unlocked a new technique of integration? Can I use this on any function I want? And that is what we'll be understanding later on in the talk, actually right away. But first, some visuals. I want to talk about convergence, and I want to talk about differentiability of sequences of functions. So I'll be building into one and the other. I wanted to talk about continuity, but unfortunately ran out of time. I mean, you're getting most of the talk still. So what I have here is a demo of what a convergent sum might look like. And so I take an epsilon to be 0.03. I project all infinitely many points. I know, infinitely. It takes a little bit. It takes a hot minute. With infinitely many points and all. And there we go. We just move it along until all the points that we have in our basket are within our epsilon range. And so you see here, the process stops, and we can conclude that the sequence converges. Of course, a visual proof like this is a bit cheating, but with enough hand-waving, it seems pretty good. And that's an interesting way to visualize, say, a convergence sequence. And the big bit here is that I can take this value of epsilon to be anything I want. I can make it arbitrarily small, I can make it arbitrarily large, and I can find a point, I can find this big N, such that all of the terms later on in the sequence fit within epsilon basket, within the little yellow brackets. And so that's the big tool of convergence that we care so much about in real analysis. And because non-examples are great for understanding a topic, here is an example of a diverging sequence. However, my animation is really lame. It goes along until we're all outside of the epsilon basket, shifts up, until it gives up. And it gives up at n equal to 23. A very lame place to stop. But I will admit I didn't go further because I didn't want to add a feature where the camera zooms. So that's just laziness on my part. The interesting bit here is that, say, if I used a tiny epsilon or went as far off as I wanted, I wouldn't be able to choose any limit here. I wouldn't be able to ever find a spot where all the terms in this sequence fit in my epsilon basket. And that's really interesting. I think it would be fun to show off part of this animation one more time, just to vibe with what's going on here. I project all infinitely many points onto this plane, which takes a little bit. I'll fast forward for you guys. And then move along until we find this value of n here, where all of the remaining points sit within this basket. And for this one, no matter what proposed value that this should take on as n goes to infinity, it doesn't satisfy that all the terms sit within this basket. So, can we apply that same process to functions? Can I use that animation? Can we talk about convergence of functions? Like, this is a rule that applies across a domain. Is there some way to talk about like a multivariable function and just take one of those variables to infinity? So, yeah, I plot out one example of a function. And the bit here is that if all these lines sit within some band, about 0 in this case, because the function is converging to 0, then we can conclude that this function converges. If we can find a point where every part of this line sits on 0, or like close enough to 0, then we win. So those are some interesting little tools there. I didn't get into very specific about what's going on in this process, but you can kind of get the gist if I hand wave enough, and we can feel a little happy. So, when we're talking about sequences of functions, the big question is, can we determine anything about the functions, the function that this sequence converges to? Can we tell what its derivative is? Can we tell the slope of the limiting function is? Not always. I bring this up because it's really important later on. We can't necessarily take every term in a sequence, differentiate it, and then see what that converges to see what the derivative of the original limiting function converges to, which is a lot of words. I know that's a lot to meditate on. But as an example of something like this, consider the sequence of functions fn such that fn of x equals n. It's every function here is constant. So if I say chose f1 of x, then that's a constant function that's just equal to 1 across all of R. So each function's derivative is 0. And this is a bit problematic because if we take n to infinity, we, in some sense, have a function that just is infinity across its entire domain. So I plug in a value, it spits out infinity. That's a little weird. And so that function has slope of 0. It's not great. It's not very fun. So that's one example of a function that we can't necessarily gain any information about it from its derivative, or the term-wise derivatives, sorry. So with those few examples under our belts, it is time to face our final boss from earlier, the type of problem that I promised we would be studying. And so this is known as differentiation under the integral sign. So if f(xt) and its derivative with respect to x, with respect to that first input there, are continuous on a rectangle, I showed an example of what such a function might look like earlier. If I can just find it. Across a rectangle. And you can see this is the rectangle 0 to 7, 0 to 7. And, if I know anything about continuity, that looks pretty continuous to me. I'm not proving it here because there's other things I want to talk about, but that looks pretty continuous on this square here. And that's the function that we differentiated earlier under the integral sign, that e to the negative alpha t. I just replaced alpha with x. And so the big crux of this argument is that both it and its derivative are continuous on this rectangle. And actually, this being a rectangle is pretty critical to the argument that I'm about to give you. And so the bit is this function whose values are determined by a regular integral from c to d, where they're both just fixed numbers, will be differentiable and its derivative will be f's first derivative with respect to its first input, x, which I have written as del by del x, f of xt. And so now, getting straight into the meat of the argument, of course, I think it would be fun to see what a proof might look like. And actually, we have more proofs than maybe I'm willing to admit in the rest of this talk. But that's okay. We'll get through it. So, using the definition of the derivative on f, we see that for every epsilon positive, we need a delta such that if its arguments are sufficiently close together, then it is sufficiently close to our proposed derivative. So if we can squeeze things together however we want, then in some sense we have pigeonholed this derivative function to be what we want it to be. And so continuing on using some standard rules of integration that you may or may not have seen already, we can just plug in the definition of f, or the big F here, pull out the integral sides. We see this and this, which they look pretty similar. I know it might not be too clear at the moment, but they're similar beasts. And so we can use the mean value theorem to see that this equals f of zt. Well, maybe not f of zt. That's another typo, actually. Z would be some arbitrary point between z and x. So somewhere between z and x, we have a point where this takes on a value of its derivative. And so because the derivative of f with respect to its first argument is continuous, we can see that we make this less than anything we want. In particular, the continuity of f's derivative with respect to its first argument on the compact set D tells us that there exists a delta such that when its arguments are close together, then its outputs are this close together, where we said choose epsilon to be whatever we want and divide it by the bounds of our integral. And so plugging this in, we have a bound on our integrand, which shows up in the final answer here. And we see that we have that it's sufficiently close together. So, some notes about that. There's something to be said about uniform continuity. Can we really make this difference arbitrarily small? Where, once again, the z should just be some point between z and x. I made a slight error there. Yes, but not with naive continuity. So there is a proof to be made here. A continuous function on a compact set, specifically on this two-dimensional compact set, which is a rectangle, ends up being what is called uniformly continuous. And we can see that with that GeoGebra demo I gave earlier. Not very easy to move around. Yeah, right here. We can see that if we have its maximum here, I'm not entirely sure what the best way to describe this is, or without using things that should definitely be explained. So we can if we make our arguments small enough together, we see that there's no point where the function changes too drastically that we can't deal with. If I ask for all the points in my function to be closer than 0.1 or something along those lines, I can find a small enough ball to keep that all happening. I'm not going to prove it for this specific case, but that is the situation there. And so we see that we were able to use this argument on that function we talked about earlier because of this compactness, this uniform continuity, which does require some more talking. I'm not going to get into here. But you might be wondering, where's the infinity sign? we might need to go back in to the proofs, because this is not equivalent to an infinite integral. It's not unbounded. It's a regular old integrand. And so we got to go back in. We use this other definition of D, which is some rectangle that's unbounded with respect to one of its inputs. One of its coordinates can just be anything off to the right of C. So we're saying that this is differentiable, and once again, we see the differentiability show up in this form, where the bounds do regular bounds thing, given that the integral in star converges uniformly, which is another flavor of convergence that I'm not really going to explain very well. And I did hope to have more demos like this, but I will go through what we have and how we might be able to intuitively understand. So our previous result works for integrals over finite regions. If C and C plus n are both less than infinity, we have regular definite integrals, then we can just differentiate like this. And so what I talked about earlier about this business of maybe we can compute, after pushing n to infinity, we can compute the integral from C to infinity, the derivative of that, by studying the sequence of derivatives. And so maybe at this point you don't really trust me very much. I'm just kind of pulling things from underneath of you as I go. But the argument goes virtually identically the same, is that we have that this sequence of functions derivatives converges uniformly. And so it does end up converging to the right thing. It does end up in the right space. So as I say here, the derivative of big F is the limit as its term-wise derivatives go to infinity, and that gives us the integrand we so desire. And now that was a lot of technology. I'll get into some applications and talk about some more fun things. That was good to get out of the way quickly. So earlier we asked if taking the derivative with respect to alpha n times is equivalent to this integral here. And barring this plus or minus 1, I just wanted to keep this equal. So we know now that the answer is yes. Or, well, no, we show that the answer is yes, because we need for this integral to converge uniformly. What does that mean? I will go through that in the bread and butter here, the actual proof here. Given that they're all continuous, the exponential is continuous, we can multiply them together and it'll still be continuous, infinitely differentiable, in fact. And so now all that we need to do is show that this converges uniformly. Then we're safe to differentiate under the integral sign. Excuse me. So here's kind of another crazy proof technique that I had to meditate on for a while. So this whole notion of uniform convergence, we need to be able to make a sort of local statement about an interval rather than a point about a function here. So given that alpha is not equal to 0, we can find a point between 0 and alpha, call it A, which we can move around as we see fit, and then observe a bound on this original integral. Call it g of t. Then, crazy part, this is going to be a lot of technology to get through, a lot of stuff to get through. We can find an upper bound on g's integral with the upper Riemann sums. And so this will converge, hopefully, as I will show. I have a sequence of functions. I'm saying that it's increasing because the integrand is positive. So f will converge uniformly if this sum converges. Because you might be familiar with monotone convergence, things like that. This sequence is monotone. It'll hit the same integral that we want to see from earlier. And we just need to show that this converges. And so we use D'Alembert's test on the sum. We see if this ratio of its k plus 1th term divided by the kth term is less than 1. You go through the algebra, you see as e to the negative a, which is less than 1 because a is positive. Now, that is a lot. That is a whole heck of a lot. But we found our factorial. Set alpha equal to 1, the denominator disappears, and just replace n with a real variable x. And we get something meaningful now. We get an integral, although an improper integral, that goes to infinity, represents x factorial across its entire domain. And so this is the fabled Euler gamma function that I was talking about earlier. It's still the most popular definition of x factorial to this day. It is infinitely differentiable. It is its second derivative is positive, which is also known as convex or concave up. And if you remember what I was talking about earlier, it is logarithmically convex, which was that note that I made earlier about how we can't necessarily, or it's hard to find a function whose, with the second derivative of its logarithm, strictly positive. But of course, there is still wild behavior when x is less than 0. And it follows that same principle from earlier that I was talking about, where we can extrapolate based on, oh my gosh, Geogebra. We can extrapolate based on behavior in 0, 1 using this type of stuff. So all of these points for negative x are poles which explode. And that Euler gamma function that we just discovered has that property, which is great. That's very interesting stuff. So it is great that this integral converges uniformly and all that. But the proof that I gave you was quite a bit more intense than it needed to be. Why is that? Well, you have an elementary function that represents this integral. It's not hard to integrate. So we could have just used something like induction to achieve the same result. We didn't need to show this uniform convergence thing to link up the left side here to the right side. The problem occurs when we want to, say, compute the derivative of x factorial and see whether or not this thing converges. It has no elementary antiderivative, so the formula cannot be derived simply using induction. Or at least not the way that I was thinking of. I have no other ideas, but I am open to other plans. The proof that I gave you earlier, though, still works for this integral. To see that we can differentiate under the integral sign, link the left side to the right side, and be happy at the end of the day. So I'm going to look more deeply at that type of situation by looking at some of the internet's many integral calculators. So we're going to put Wolfram Alpha up against Integral Calculator. Very creative name, I know. And you see Wolfram Alpha's answer nice and quickly. This nice representation with respect to the Euler-Mascheroni constant. And the indefinite integral, which involves this EI of negative t, which is interesting. We can go over here and see what happens over on Integral Calculator. And it works through. It also decides that its antiderivative involves this E1 term, which, once again, is not elementary, does not have an elementary antiderivative. As you can see by, it gives you Wikipedia articles on each of the constants that appear in the solution. And you can see the Risch algorithm shows that EI is not an elementary function. I know nothing about that. This is just what this is telling me. And I don't know, I'll trust it to implicitly for the time being. Hopefully one day I'll understand. And so if we want to compute the general antiderivative of this, say t to the x, without fixing x, to see the slope at 1, we see Wolfram Alpha gives us this very, very strange answer, which I don't really know how to interpret. And integral calculator also does not fare very well. Gives us a similar type of answer involving what is this? I think the digamma function, polygamma function. I also do not know much about that, which is something to look into. So it's this is a bit unwieldy, whereas what we dealt with earlier could have been dealt with, or could deal with this. And so now I'll show you why we might care about the solution that Euler gave us back in, I forget what year it is. You can do the math here to see. 1992 minus 193. But this is a fairly recent proof. Why is that? Well, it took a while for people to figure out that the logarithmic convexity is the interesting property to study here. It's concave up in a really strong way. So not only is its logarithmic convex, but that necessarily implies it is convex. And there are other convex solutions to the problem that I gave you earlier. None of them will be logarithmically convex or concave up. And so here, I just need to chat with you very quickly about convexity. We have this relationship between, difference quotients of concave up functions, which we'll be making heavy use of. And here I have a small animation of that. Looking at these 4 points, as long as this point is less, or as long as this one is greater than this one, and this one is greater than this one, we see that the slopes follow this relation here. Not very specific for me to say it, but there is a hand-wavy visual proof to be seen there. And to get into the proof, it's pretty much just standard algebra at this point. We plug in the natural log of f at n for these intervals here, just using this property here and the fact that the natural logarithm of f is concave up. So it should deal with what we have earlier. We plug that in. F at natural numbers should be factorial values, as 2 describes here. So we have this relationship between this staying the same over here. We have like a bracket, shall we say, about this middle expression. So now the big question is, does the terms on the sides, does this simplify and does this simplify as well as this? And the answer is good news all across the board. They do simplify. And you can go through the work, you can see f of a natural number is n factorial, and you have this difference, which you can expand out in using repeated multiplication, that key factorial property that we talked about earlier, and then use a property of the logarithm where multiplication can be written as addition. And then this all cancels out. We get the ln of n. And now, playing the same type of game with f of n plus x, we just can't replace f of n plus x with n plus x factorial. And just have f of x here, removing all of the extra natural number stuff on the side. And now we have this sum, which we can plug in to the relationship we had earlier. Multiply everything by x and sub in the expressions we had from before, which gives us these nice relationships. It's just algebra at this point, and I'll let you do that. And go through and see that this all holds. And so now we have 0 on the left, a whole stinky function in the middle, and then something on the right. We have bracketed what is on the inside, given that our right bracket will be moving. So now, if we take the limit as n goes to infinity, we see this stuff on the right have 1 of 1 plus 1 over n, which goes to 0. And so we have this relationship where 0 is less than or equal to this difference, which is less than or equal to 0. And there's only one thing we can conclude at this point, is that f equals what it's being subtracted by. And so we use something like the Squeeze Theorem to show this. I'm not going to prove that. Like some of the many other things, you might have been able to tell that some of the difficulty things are a little funny in this talk, but it is what it is. And so what we have here is that we have just derived the Gauss product formula, which this expression is very similar to the one that Euler originally discovered back in his day, which he then used to eventually find this integral representation on the side, which I'll show you here using the Wallace product. And so it's a pretty common, or well, an old fact in mathematics, I guess old being like the 1650s, I believe. I should probably be checked on that. We can use the Wallace product, which converges to pi. And Euler originally found some relationship here between pi and this limit expression that he had computed. And then use that to deduce that usually quadratures, integrals, do the same type of thing, where they just give you pi for something. So that led him from a hunt here to here. And so now to compute pi as a final goodbye, I guess, a big bang at the end. The Gauss product here, when we plug in a half, we get a half factorial equal to the integral from 0 to all this stuff. It's just replace the x's with halves. And using some, I'll leave it as an exercise for you to figure out that the integral from negative infinity, or well, to figure out that a half factorial, this integral here, is related to this integral here. The Gaussian integral. And so now we have this relationship, which is nice, very nice. Square root of pi over 2 equals this limit. So if we were to square both sides, assuming that this right side converges, we can multiply in the way that I'm showing here. Pull out these n's to the front here, and then just represent the factorials as the repeated multiplication of whole numbers that I was talking about earlier. And on the bottom, pull out a bunch of halves to get these representations. Odd numbers on the bottom, not even numbers. Odd numbers on the bottom, factorials on the top, this square rooty thing, and a bunch of halves. We move on. We multiply the top by 2 to the 2n minus 1, which we distribute into all of the factorial points here. And we get a bunch of even numbers on the top, odd numbers on the bottom, which is almost what the Wallace product has on it. It's just there's some factor of n on the top here. We have 2n minus 1, whereas over here we have 2n. So then we need to massage the square root on the left. We move along, we see that pi over 2 equals this limit as we note that this square root here goes to 1. And then we can just move the n over there. And we get what we want to see. Oh, yes. I want to note that this equals pi over 4. So we multiply both sides by 2 to get this 2 in front of the n. Move that over there, and we have the Wallace product. And so just to show that I am not just BSing you, I'm going to make a small Wallace product function in Python. So I'll just from math import star def w of n. That'll be our function here. And so we'll want to take the product of a list. Of course, I'm going to be using a list comprehension here. I'm very cool. So it'll be something for in range the values of n between, or the values of k between 1 and n. And so just looking at what's on the leftmost side here, we have 2n times 2n divided by 2n minus 1 divided by 2 times n plus 1. There's some syntax errors here. And yeah, if we return that, and now I just want to see how far we can go. In order to verify that this works, let's see what Python says. I see that, yes, so this equals pi over 2. I'm going to need to multiply the output by 2. And at 10, I hit the backslash, and that's giving me funny output. So yes, at 10, it's a terrible, terrible approximation. Let's just slap another 0 on there. We start to see something a little better. We might actually be seeing that I have a bug in my code, unfortunately. What is the situation here? Yes, these are n's when they should be k. Very silly of me. It happens. It happens to the best of us. And we see 3.14, which is excellent. That's wonderful. And now we see how far we can go. 3.1415. Wonderful. Let's slap another 0 on there. Even better. How far can we go? This is what I love to do with my code. There was a little bit of a lag there. This might be the one that kills it. And it's the one that kills it. Because I think it would be very fun, I'm going to open my activity monitor, go onto resources, and just watch my RAM usage as we move along. You can see the orange line saying my RAM usage. Oh, no, wait, no. That isn't the one that killed it, actually. We need one more 0. That led a little bit of a dent. And now we're seeing my RAM skyrocket. This is just a bit of fun. It's not exactly related to a bunch of the mathematics that we were going over. You can see that the way that I'm computing it is not especially efficient. We get a couple digits of pi. I'm going to kill it before it uses up all my RAM. And yeah, that'll be the coding. Yeah, so that does converge to pi over 2. And as some homework, I would like you to check where does this function equal 0, where we're using that x factorial function from before, taking all the negative values 1 over x factorial, or the negative integers of x factorial explode. So reciprocate, we should see that the negative integers of x factorial should hit 0 when reciprocated. So what other familiar function has the same set of roots? And then now use the value of x factorial from before to conjecture a striking relationship between the factorial function and a well-known function from trigonometry. So this is a bit of a fun. And yeah, that's everything that I have for my talk, I'd say. Hopefully I wasn't blatantly wrong. too many times. Yeah.
Okay, great job. Do you still want that function between 0 and 1?
Oh, absolutely.
Okay, I wasn't sure when I was supposed to cut in. Mahmoud and Viom collaborated on this one to go with e to the negative sign of 1 over x. And then this one has to be piecewise, of course, where at x equals 0, this is equal to just 0. And then otherwise.
Interesting. I might need to see it in text form, but I am absolutely enthralled about that.
I'm sure to get this to you without opening DMs.
I guess I can. Yeah, I can check on this. I think I just need to go and open it quick. Yeah, just to make sure that I'm not. It's very surprisingly hard to listen to mathematical formulas. Oh my goodness.
Is the chat still there? Do you need me to put it back in?
Oh, I have chat on my phone.
Technology, I love it.
Yeah. So this is e to the negative sign of 1 over x. Very interesting. X of sine 1 divided by x. And to deal with the discontinuities as well. That's discontinuous on 0. So I guess if x is not equal to 0, people really hate Python syntax for some reason. Else 0. Let's see if this decides to work. Interact. Man, I'm chugging away. This will be interesting to see for certain. Ooh, that's a really wild one. Let's just stop it here. So yeah, it explodes over on those sides. I'm going to use. I'm going to cut off earlier before the discontinuities on the left and see what Manum spits out for that. And then we hopefully see it. Oh, never mind. I have made an unfortunate mistake. I want the y max to be, let's say 10 for now. And then y min.
Mahmoud wants a fix of the discontinuity. Mahmoud would like e instead of 0.
Ooh, interesting. Can see how that pops out. I know Manum is not going to be very funny about it. Like, it's just going to connect it unless we be really explicit about what goes on. Excuse me. And actually, graphing with discontinuities is kind of broken in Manum at the moment, which was frustrating. I don't exactly remember how to zoom that y min y max thing. I might need to reference some of my other code. Yeah, so we still see psi being a function here. I like this behavior over to the side there. If only I could zoom in on it, which I should have in a moment. Yeah.
We have a comment in chat. It's we have a positive sign over 1 over x, not a negative sign. In the yeah, there we go.
Pardon?
We need a negative sign
Oh, I gotcha. Interesting. Yeah. I don't exactly remember how to zoom in. Yeah, that is really unfortunate. It's kind of hard to zoom in without doing a bunch of extra work for some reason. You know what I'm going to do is I'm going to just go to a different piece of code that I made up a while ago. Thumbnail. And I'm just going to replace it over here. And it might take a little bit longer to render, but it'll be okay. Yeah. Pretty cool. Just chugging away here. The unfortunate thing about MANM, specifically on my computer, it does get the full render. What goes on there. I could probably go do some fiddling so that it doesn't always export to 1080p 60 FPS, which is a bit excessive at the moment. We're almost there, I think.
Guess I can ask chat now that we're just messing around with the coder here. If there's any more questions for Shawn about all this fun stuff that we've been talking about.
Oh, wow. That is really stinky. Oh my goodness. MANM did not like that. Yeah, you can see the crazy behavior sine of 1 over x displays as x gets close to 0 just before the piece changes. And we extrapolate just the right way.
Robert is asking if this is the 3 blue 1 brown program.
Oh yeah, it is. That hip new MANM stuff.
Yeah, Robert, you're gonna have to learn the code to try this one out. Sorry.
Yeah. Unfortunately, but I guess my general review over MANM is pretty similar to 3 blue 1 brown's review. You probably you'll have more fun if you just try to use Geogebra at the moment, where Geogebra is the program I used earlier to show off that function earlier over the rectangle. Oh, yeah, right here. Just blinds your eyes for a moment, but those dang light themes. So yeah, you'd probably be having a lot more fun animating using. But don't let me stop you from making some interesting looking MANM animations.
All right, so we haven't been getting much activity in chat, just Robert screaming for help by seeing code. But I'm going to flash my camera on. I'm going to be back here. I'm just going to clap for Robert. And just clap at home. I know that you all are doing that. This is a great talk, a very great visuals. I know that you did get some praise from Steve earlier about the visuals as well through Robert. But yeah, thank you for bringing us back this semester. That was a great look at this. Just one last call for questions, or else we'll stop in about 30 seconds. We'll hear.
All right, I'll leave this up as like the final look. Yeah, thank you, Robert.
All right.
Yeah.
Thank you all for joining us. This has been our 5th MS Cube Talk, and we'll be back in exactly a month. I believe we've just booked our next one on the 10th of next month. We've gotten confirmation on that, as well as another Math Club Talk on the 24th, Pi Day events happening sometime in March, as well as just other things So just keep posted and keep up with MS Cubed. We have some fun things for the rest of the semester. Have a good night. Have a